down here, but I still want to do a little bit of a review. So let's go back to kind of looking at some probability stuff. So let's start with problem 5. Okay? So it starts out, and this is kind of the way that the exam will flow as well, is I might give you some information and say, use this for the next 5 questions. Okay? So we're going to be using this table for the next 5 questions. So on number 5, let me, so we can see this all a little bit better. We're going to use this contingency table that gives us kind of these 2 events. So whether or not someone wants legalized or marijuana legalized or not, and then whether or not they're age 55 or older or not. Okay? So remember, kind of the total columns tell us the probabilities of whatever the events are on the row and column heading. So the probability someone is 55 or older, if we selected someone at random, would be 0.25. Right? The probability they don't want marijuana legalized would be 0.34. We then said these top 4 left cells, right? I guess maybe to kind of make this all look the same. These top 4 left cells all represent the intersections of whatever the row and column heading are. So the probability someone's 55 and older and wants marijuana legalized is 0.14. Okay? So that's just kind of a little bit of a review of these contingency tables. So what would the missing value of X be in this contingency table? Well, how did we say first of all, which of these can I rule out right away? If I'm looking for a probability, yeah, 1.27. I can't see anything outside the range of 0 to 1. Right? So right away, I now have a 1 1/3 shot if I'm just guessing, just from simply remembering that principle. So on these multiple choice, I think sometimes students don't like multiple choice questions because they seem, or they well, if I get it wrong, I get, but on a multiple choice question, simply remembering the principles can allow you to kind of rule this out and make, even if you're guessing, give you a lot better chance. Whereas on a short answer, knowing those principles don't get you any closer to kind of being able to work through the problem, right? So we can rule out D, but how can we find X? Well, if we remember, how do we find the totals here? Like, let's say I left off this entire total column. How could you reproduce those totals? Yeah, add across the rows, or if I had deleted these, add down the columns, right? So notice 0.14 plus 0.11 is 0.25, which means 0.52 plus X should be equal to 0.75, right? So instead of kind of switching, because it wouldn't really have to write a whole lot here, what we have is 0.52 plus X is equal to 0.75. Now from here, just a little bit of algebra, right? Subtract 0.52 from each side so that we would have X is equal to 0.75 minus that 0.52, giving us that 0.23 value. Okay? So X there would be 0.23. Okay? Any questions on that? Like I said, something else I maybe could have done, we'll use a different letter here. What if I had left that out? How would I find what Z is? 0.14 plus 0.52 would have given me that 0.66, right? Or Z, if I had left that part out, okay? Any questions on that? Shouldn't be too bad. This should hopefully be an easy one if I asked you this on the exam. So what's the probability a person is 55 or older and they do not favor the national legalization of marijuana, right? So if I'm looking for an and, right, what I'm really thinking about there is the probability of an intersection. We said the top 4 cells represent the intersections. So the probability someone is 55 or older and they do not, right, favor legalization. So that would just be this cell right here, or that 0.11. So that one, I mean, there's no real work to do there other than being able to interpret that and kind of use that contingency table to find that intersection. Okay. So hopefully those are some easier points in the exam. Now we'll get to some maybe a little bit more difficult things. Right? So given that a person believes in the legalization or wants the legalization of marijuana, what's the probability they are 55 or older? So let's think first about what we want. So I'm going to switch over here. This might take a second. Let's see if we can get this to show up for everybody here. 1, 2, 3, there we go. So what we wanted was, I already forgot, I think it was given, right, that someone wants marijuana legalized, what was the probability that they were greater than 55 years old? Or you could put here, like, you wanted to write it out, you know, older than 55, right? That was our event. Okay? So here we're looking for a conditional probability. And I'll show you where we find this in the formula sheet after we kind of switch back, right? But we have the general form is that if I'm looking for a conditional probability, that's going to be the intersection of the two events divided by the probability of what I'm conditioning on. Remember, what I'm conditioning on, it's what's on the right-hand side here, okay? So if I write this out in the context of my example, right, this is my A, this is my B, I'll find the probability that someone is older than 55 and wants marijuana legalized divided by the probability of whatever I'm conditioning on, which I was conditioning on, the probability that they wanted it legalized. Right? What this is really saying is take all the people who want it legalized and what proportion of them now are also older than 55. Okay? Well, we can find these two things from the table, right? So let's go back, and what I'll do here, share my screen, but I'll leave this up down here in the lower corner so if you're kind of still writing some things down, we'll have it up there as we look at this. So first of all, where did I get this general form of the equation? Right? If I look at this formula sheet, we'll zoom in so we can see things a little bit better here. Right. Over here on this right-hand side, oh, thank you. Gave you guys a little more time to write it down then. So if we have our formula sheet sometime today. There we go. Over here on the right-hand side, we have that the conditional probability is the probability of the intersection of these two events divided by the probability of what we're conditioning on. Okay? So that's how I got the general form of the equation to solve for the conditional probability of A. So then, if I go up here to my contingency table, I want the probability that someone's older than 55 and they want marijuana legalized. So older than 55, want marijuana legalized, so yes and yes, 0.14. So if I'm thinking about here, I'm thinking 0.14 is my numerator. And then the probability that they want marijuana legalized, so that's just yes, they want marijuana legalized, go down to the total, right? That would be what, 0.66. Okay. From there, it's just simply enter this into our calculator. Can't do that one off the top of my head, so I brought my calculator today. So this should be approximately 0.21. Right. Any questions on that? So if we come down here, look at all the possible answers for 7. It's approximately 0.21. Now, sometimes like in this one, let me see, I think the exact answer would have been like repeated. So if I only show you the answers to 2 decimals, then whatever you come up with, round it to 2 decimals, right? So this would round to 0.21. So that's kind of the answer that we choose. Now, I'm never going to, give you like 0.21 and 0.22 so that if you make a rounding error, you get the wrong answer. And I'm not going to never be that mean. But however the answers are displayed, that's what you should kind of round your answer to. Okay? Any questions on that one? Or we're okay with that? So there's nothing in the chat here. Okay. So here's where, maybe it's a little bit tougher because we're writing things out in the probability, or we can't just write out our events now. So I'm kind of giving you these events where O, I'll tell you up here, kind of represents being older than 55, and LM represents wanting marijuana legalized, right? So not wanting marijuana legalized would be LM complement. Okay? So if we want these two things, right, if we're worried about, are they, first of all, let's do 8 and 9, because 9 is a lot easier. We'll spend more time on 8. If I'm asking you, is wanting marijuana legalized and being under the age of 55, so that would be O complement, are they mutually exclusive events? Right? So the only way we have mutually exclusive events is if those two things can't happen at the same time. If they can't happen at the same time, then their intersection has to be what? Two things can't happen at the same time. The probability of seeing both of them happen at the same time would be never, which is a probability of 0, right? So what we know, we're thinking about the definition of mutually exclusive, just more generally, not in the context of this example, is that the probability of the two events, the intersection of those events, has to be equal to 0. Well, here we had kind of is being not over 55 or O complement, and wanting marijuana legalized, right? Are those mutually exclusive? Well, the intersection, if they were mutually exclusive, would have to be equal to 0. Okay? Well, if we go up here, first of all, no matter what events I asked you about, did we have any zeros for the intersections? No. So it doesn't matter which of these I ask you about, none of them are mutually exclusive, right? The only way they're mutually exclusive is if I see an intersection of 0 up here in one of these top 4 left cells, right? More specifically, what we were looking at being not older than 55, so under 55, and wanting marijuana legalized, right? So we know the intersection is 0.52, right? But simply remembering the mutually exclusive definition that it's when we see 0 intersections that have a probability of 0, well, right away we know that, no, none of these can be mutually exclusive. We have no zeros in that contingency table. So right away, we can rule out A and B. So here now we're looking at no, they're not mutually exclusive. And then we're really just choosing between, is it because the union's equal to 0 or not equal to 0, or is it because the intersection was not equal to 0? Well, we just said they're only mutually exclusive if the intersection is 0. So here, they're not mutually exclusive because that intersection is not equal to 0. Okay? So there, even if I, just look at the table and see there's not zeros, doesn't matter which two events I'm talking about, I could have ruled it down to C and D, and then I know, well, the only way I can identify mutual exclusivity is if the intersection is equal to or not equal to 0. Right? It doesn't matter what the union is. Okay? Any questions on that one? So if you're watching these, and this goes to, people showing up, putting effort in, and trying to do well. Hint, hint, you're always going to be looking for the intersection when you're thinking about mutually exclusive events. These unions, we should have been able to rule out right away. It doesn't matter what the union is, right? It only matters what the intersection is. Okay? All right. So this one's a little bit more difficult, right? So let's think about independence, okay? If supporting the national legalization of marijuana and being 55 or older independent events. So we're thinking about event O and event LM here, right? Being over 55 and wanting marijuana legalized. So the only time that two events are not mutually exclusive, independent. Let's see if I've got, well, here's one way we can check. Right? One of the checks was if the intersection is simply equal to the probability of each event multiplied by each other. So kind of thinking about here are special conditions. This holds. Right, might be a good thing to write down next to it, or if we're kind of thinking about in the future. This only holds if the events are mutually exclusive. Why? Because the union is supposed to be the probability of both events minus the intersection. Well, if the intersection is 0, then this is what the equation becomes. So this only holds if they're mutually exclusive. And in fact, just to kind of prove that, so we could actually use our previous example of mutually exclusive and see if that holds, right? So, well, we already know it won't, never mind. It doesn't matter for us to check because we already have talked about it doesn't. But if we had found the union of those two events and kind of added up the probability of each event occurring, we would have found that those two things weren't the same, right? So they weren't mutually exclusive. But for independence, this is the special condition that'll hold, okay? So if they are independent, this equation will hold. If they aren't independent, then these two things won't be equal, right? So let's use that one first. Okay, so let's go back. We're looking at this table. What that equation, that special condition is saying is if A and B is equal to simply the probability of each event multiplied by each other, we know they're independent. So for us, this would be older than 55 and wanting marijuana legalized. If that's equal to the probability of being older than 55 times the probability of wanting marijuana legalized, then these will be independent events. So if we look here, what's the intersection? So older than 55, wanting marijuana legalized, 0.14. What's the probability of being older than 55? We go over to the total, 0.25 times the probability of wanting marijuana legalized, which is is it 6.6? Yeah, 6.6. So if I do this math right, 0.25 times 0.66, I get what? 0.165. Are those two things equal? No, so they can't be independent. Right? Now, that's a way to check to see if they're independent. The problem is the answers that we have here, so that might be good for a short answer, but here I've got the actual definition of independence, which is that, kind of leave this up here. The actual definition is if the unconditional, right, probability of A is the same as the conditional probability of A, then these are independent events. It doesn't matter if we know that B has occurred. Right? So we're thinking about this in the context of our example. Let's say if the probability of being older than 55 is the same as the probability of being older than 55 given that they want marijuana legalized, right? I'm just writing this out, kind of the definition of independence in the context of my example. Right? If this holds, right, then I know that they're independent. If it doesn't hold, so here is if that holds, they're independent. If it doesn't hold and they're not equal, we would say that they are dependent or not independent. Now, the way that we kind of have this here, looks like there's one of those right there, right? Anytime we're checking for independence, remember, it has to be at the probability of the thing on the left side of our conditional line. That's what we're still looking for the probability of. So this first part of my conditional probability should match up with whatever that unconditional probability is. So this one makes sense. I don't know if it's the correct answer yet, but at least it makes sense. Well, here I'm comparing the probability of LM to the probability of O. Well, that doesn't make any sense. I have to be comparing the conditional and the unconditional probability of the same event. So right away we could rule out B. Here, same thing. We're comparing two different events. That doesn't make any sense. And then down here, we're comparing two different events. We actually can rule out every single answer here without actually even checking with the numbers, right? Now, what if I instead had, flipped one of these so that we actually did have to check it? So maybe I was doing down here, oops, maybe something like this. And so now there are two viable answers, right? How would I actually check it here? In the original, we could rule it all out, and we know that A has to be the right answer. But how would we actually check it if we had multiple answers that kind of made sense for checking independence? Well, what's the probability of being older than 55? Go up here, older than 55, 0.25. I'm not on the screen. So 0.25. What's the conditional probability? Well, we can't just get the conditional probability directly from the table, but earlier, let's see if I have it over here, right? We'd actually solved for a conditional probability already. In fact, just to save us some work, I actually already solved for this conditional probability, right? The probability someone's older than 55 and wants marijuana legalized. So I know this equation would give that to me. I could go on the table, look up these values. I end up finding that probability is that 0.212, which we rounded to 0.21. They're not the same value, so we say, no, they're not independent because this conditional probability of O is not the same or not equal to the unconditional probability of O, or being older than 55. Okay? So this is a situation where we can use some of the previous work we did to actually save us a little bit of time as we're working through this exam. Okay? Any questions on that? No, that one's a little tough.
I see the equation on bottom, 0.14 and the
Oh, yeah.
0.65.
This one? So this was where we said this is an additional check. Like this would be, to me, if I didn't have a multiple choice where the answers were given as like the actual definition of independence, using that special condition, if this was like a short answer question, probably the easiest way is to check it using this, right? Because all these three components are very easy to grab from that contingency table pretty quickly. Okay? And then if that equality holds, they're independent, but like in this case where they don't, then we would say they're not independent. Any other questions on that? You want to see something again there? Or?